Hi, everybody. Today's topic is going to be a topic referred to as special triangles, or specifically special angles. And what we're going to do is we're going to kind of make the next leap in our study of trigonometry. Up until this point, we've really been working in that red, which is a very practical setting. You guys have been working your way through solving for properties of triangles. And we've been able to apply that to certain situations. In all of those cases, since it was very practical, then we needed to talk about it the way we practically would, which meant that we were using a lot of approximates. In most of our cases, our final line when we were solving for anything was rounding off to a decimal approximate. Today what we're going to do is we're going to make that leap. And instead, we're going to start to talk about some things in a more theoretical stance. And so, if we're going to address things theoretically, then we need to start to work more towards exact values for things. And so what we're going to talk about today are some special angles that we can work our way through that enable us to talk in exact terms. So, first thing I'd like you to maybe come across is our first special angle. Now, I want to be clear, this doesn't have like a number one in a hierarchy, but it's the first one that we're going to address. And so what I'd like you to focus in on is the idea of us examining a square. And so when we examine a square, then we know what makes that a square is that there's a right angle in one of those corners, which then means if all side lengths are equal, there is a right angle in all corners. For us to examine a special triangle, then we're going to construct a triangle out of that square. And one way that we can do that is to deal with the diagonal. We should be good that once we create that diagonal, we've now created a 45-degree triangle. And so all I'm going to do is I'm going to now slide out of that diagram. And so I'm going to draw that triangle that we just developed. It's a right triangle, and we know that there's a 45 degree in the angle. We also know that that's going to make that other angle 45 degrees as well. We get to that point, and the last property we want to make sure that we emphasize was that since that was the diagonal of a square, then those other two sides are equal, or more importantly, the two shorter side lengths are equal. So, for us to take a look at that blue triangle, I think we should already be able to talk about an approximate value for one of our trig ratios. Right now, if I was to ask you, what is the tan of 45 degrees? I think I'm going to have some people who would be able to give me that value without using their calculator. Take a look at the blue triangle and see if you can come up with the exact value for tan 45 without a calculator. Okay, now what I want everyone to do, regardless of whether they were able to come up with a value, let's push some buttons on our calculator and just get a decimal value for the tan of 45. Okay, everybody should have found out that that was equal to 1. And we should be okay to take a look at that blue triangle and see why. Because this one shorter side is equal in length to the other shorter side, that when I calculate my opposite divided by my adjacent for that 45 degrees, I know that I'm always dividing by the same thing. And any time that I have a fraction where my top is equal to my bottom, I have a value of 1. Now, maybe we have to go one step further and say, well, let's put some dimensions on those. So pick any number you want. Let's say I said that my opposite side had a length of 5. Well, my adjacent side would then also have to have a length of 5. And therefore, when I calculate the tan of 45 degrees, I know that it has to be opposite over adjacent, and there's my value of 1. Now, as we work our way through, perhaps the easiest thing that we could have labeled those sides with, if I was to now get rid of those 5s, If I asked you, what's the easiest number to work with that could represent the side of a triangle, my guess is most people would come in with a length of 1. Easiest number to work with might have been 0, but I can't have my triangle with a side length of 0. So in that instance, notice we would have had the same thing, 1 over 1 as opposite over adjacent, which equals 1. Now, because I'm using those easiest values, I have an option to be able to go through and find my other trig ratios. So given that blue triangle, I think some people are going to be able to come up with what the value of sine 45 degrees is, and what the value of cos of 45 degrees is. Notice both of those ratios are going to require knowing the hypotenuse, but because we already know 2 side lengths on that right triangle, we should all be good to be able to find the length of the third. No, we're not using trig for that. I'm going to hop out right now and state, well, if I'm going to need to find the length of that hypotenuse, maybe I call it C, I know that I can use Pythagorean to be able to work my way through. And so relatively quickly, we should be able to come up with the length of that hypotenuse being root 2. And now that we have an exact length for that hypotenuse, you could now state that the sine of 45 is opposite over hypotenuse, and the cos of 45 is adjacent over hypotenuse. And you've now come up with your other 2 trig ratios. Now, really quickly, go ahead and punch into your calculator what the sine of 45 is. Burn that decimal in your brain. And now, go ahead and calculate what 1 divided by root 2 is. And we should see we get the same value. In fact, depending on what type calculator you have, your calculator may automatically give you an answer of 1 over root 2 when you punch in sine 45. Okay, now that we see that, I hope that we can recognize we have 3 trig ratios that are exact for a 45-degree angle. The sine of 45 is 1 over root 2, cos of 45 is 1 over root 2, and tan of 45 is 1. Now what I want to do is I want to jump in and look at another special angle. So what I'd like everybody to do is to use their calculator and just punch in sine 30 right now. What you're going to see when your calculator shows an answer could be 0.5. And some of you are going to show the fraction form or simplest fraction form for what 0.5 is, 1/2. And so that's somewhat unique for us. We're used to punching in a trig ratio and getting a really ugly decimal across the screen. And in this case, we punch in the sine of 30 and we get exactly 1/2. That's going to be useful for us because we can use that ratio then to create the value for other trig ratios of 30 degrees and be able to talk about those in exact terms as well. So, since we know that 30, or the sine of 30, is equal exactly to 1/2, and we know that sine is always opposite over hypotenuse, then we can go through and we can construct our 30-degree right triangle. And I know then that my opposite side has to always be 1 as my hypotenuse is 2, or my opposite side has to always be half the length of the hypotenuse. And I can use those labels just as we did before with a 45 degree to go through and find the length of that third side. And so if I hop in and I deal with my Pythagorean, then maybe I know that 2 squared is going to equal, let's call this other side x squared plus 1, and so 3 equals x squared, and x equals root 3. So I know then that that third side has a length of root 3. And so the three sides of my 30-degree triangle would be 1, 2, and root 3. And so I now have the ability to state the exact values for those. That the sine of 30 degrees is my opposite over hypotenuse. That the cos of my 30 degrees is adjacent over hypotenuse. And the tan of 30 degrees is opposite over adjacent. And I can then state the exact value of those trig ratios for an angle of 30 degrees. So really quickly, just as we did before with 45, punch those into your calculator and see that the cos of 30 is exactly equal to the same value as root 3 over 2. And the tan of 30 is the same value as 1 over root 3. We've just added in our second special angle. That we can talk about our trig ratios for 30 degrees, and we don't need our calculator to do it. We can talk about it in exact terms. Now, the nice part is, once we've gone through and we've examined a 30-degree special triangle, you actually know a third special angle as well. Because the third angle inside that triangle would have to be a 60 degree. And now, from the perspective of that 60-degree angle, you have the ability to determine the sine of 60, the cos of 60, and the tan of 60 without a calculator. So what I want you to do, pause the video right now, go through and write down the three values for those ratios. Okay, we're back. So the sine of 60 would then be opposite over hypotenuse. The cos of 60 would be adjacent over hypotenuse. And the tan of 60 would be opposite over adjacent. And of course, we don't have to write root 3 over 1. We can just write root 3. So what we've now addressed are three new angles, or three angles, where we can deal with the trig ratios without using a calculator. Talking in exact terms, no rounding. So, to sum up these two kind of areas, you're going to need to remember, unfortunately, we got to remember that when we're talking about a 45-degree angle, that the three sides of that special triangle are 1, 1, root 2. And then when we talk about a 30-degree, their three sides are 1, root 3, and 2. And a 60-degree, their sides are 1, root 3, and 2. Unfortunately, for both a 30 and a 60, you have the same side lengths. And so it then becomes, well, how do we label our triangle for those side lengths? And what I want to talk to you about is a little bit of a strategy, and it comes back to what we used when we dealt with solving using sine law and cosine law. You then have this 30-degree triangle and this 60-degree triangle. And rather than trying to memorize the location of those values, let's use some reasoning so we never have to worry about forgetting. When you take a look at that first triangle, our 30-degree right triangle, remember, small angles make small opposite sides. Big angles make big opposite sides. And so when I'm trying to think about how am I going to label those triangles, then all I need to do is look back up into my three side lengths. So I know that the 2 is going to represent my hypotenuse. That's never an issue. So I can almost forget about that. I forget about it so much, I don't even write it down. So I'm going to use the angle to determine the opposite side. So the only thing I need to look at is, which is bigger, the value of 1 or the value of root 3? And pretty quickly we should realize root 3 is larger than 1. And so when I'm going to build my triangle, the 30-degree small angle means it has to have the smallest opposite side. My smallest opposite side is 1. 60 degrees is my biggest special angle, which means it needs the biggest opposite side. and therefore root 3. And if I can keep that reasoning in check, then you can label those triangles pretty quickly every time. So, if I ever had to go through and deal with labeling those triangles, which we will all have to do many, many times, then if I start on the left triangle, if I have a 30-degree angle that is the smallest angle, it means it has the smallest opposite side. Well, now I can just fill in the rest of the triangle. Root 3 is the other side there because I know 2 is my hypotenuse. Now I jump to a 60-degree triangle. 60 degrees is my biggest angle. That means it needs the biggest opposite side. And now I just fill in the rest. I know that 1 must be the other shorter side because 2 is the longest. We want to be able to go through and be able to label the sides of our special triangles pretty quickly. Now we're going to see where we're going to start to use them. So you can see that what we're going to do is we're going to give you expressions, and we're going to need to have the ability to be able to calculate the value using trig ratios, but no longer rounding. We're going to need it in exact terms. So you take a look at that big ugly expression that you see on your screen. You have to determine the value of 2 sine 45 degrees times tan squared 60 degrees plus sine 30 degrees cos 30 degrees. In the past, if we were ever to throw something at you like this would have been a button pushing exercise. Now, we are doing this without a calculator. We have the means to be able to go through. So, first thing that I recognize, I have to come up with the value of sine 45. So, that means that I need a 45-degree special triangle. And I remember 45 degrees is the exact diagonal of a square, which means this side and this side are both equal, and therefore my hypotenuse is root 2. And so I can go through and I can plug in the value of sine 45. I know that it is exactly opposite over hypotenuse. Okay, the next item, tan squared 60. Okay, well first off, we need to make sure that we're good to interpret what tan squared 60 is. When we write tan squared 60 degrees, what that really means is calculate the value of tan 60 and then square it. You might ask yourself, well then, why don't we just write tan 60 degrees squared? And I want you to see where that could be a little confusing. If we just put that squared there, then there's a little bit of confusion of, well, did you want to calculate what the value of tan 60 was and square it? Or did you want me to square 60 and then calculate the tan of that? Mathematicians are lazy and they want to come up with easy ways to be able to write things. And so, by writing the squared on the trig ratio and not on the angle, then everyone knows that you need to square the value of the ratio. So, I'm just going to get rid of that whole portion now because we've been asked to deal with a 60-degree angle. And to deal with that 60-degree angle means I need a special triangle. So, if that is a 60-degree angle in there, 60-degree angles are my biggest special angle, which means that needs its biggest opposite side. That means 1 and 2 are my other two sides. And so I can calculate then the tan of 60 degrees, which would be opposite over adjacent. Now that says square it. And we can just proceed all the way along, filling in the values for the rest of those ratios. So, pause this video as soon as you feel comfortable to give it a try on your own, and we'll see if we match up in the end. Okay, so my next one is dealing with a 30-degree special triangle, which means I need my 30-degree special triangle. 30 degrees is my smallest angle, which means I have my smallest opposite side. Now I can fill in the rest, and I can now determine what the sine of 30 is. So for me to go through, my sine of 30 has to now be opposite over hypotenuse, and my cos of 30 would have to be adjacent over hypotenuse. And there's how we can go through and we can come up with values, exact values, for every one of those trig ratios. Well, now that you have that, the rest of this is about simplifying that to proper form. So I want everybody to pause the video right now and try to get down and match up with the same thing. Okay, we're back. So everything that I'm going to plug in red now is about simplifying. So maybe the first thing we might do is deal with the 2 times 1 over root 2. I can now take that and multiply that by root 3 squared, which is just going to simplify to 3. I then can multiply these two fractions together and get my root 3 over 4. Well, I can fully simplify the first term into 6 over root 2, and now I have to add to that root 3 over 4. Now, we may differ here because some people may choose to get a common denominator of 4 root 2. Other people may not like that radical on the bottom and then say, okay, so what I'm going to do is I'm going to rationalize that. You do not have to show this line of you multiplying the top and the bottom by root 2. We're now at a point where we should be pretty comfortable to rationalize that without writing that line down. So please feel free to come in on something like 6 root 2 over 2. And now to get a common denominator, I should be able to get a denominator of fourths if I double everything in my first numerator and add on my root 3. So hopefully we got down to the same thing, we matched up, and we're good. So there is an application for us as to how we can go through and we can use special triangles to come up with the exact value of trig ratios. So one last thing, only talking about expectation. If we were to ever ask you, for instance, what is the tan of 30 degrees? Well, you can look in your green triangle and you can see that that is equal to 1 over root 3. I want you to notice that that trig ratio might be considered in bad form because we have a radical on the denominator. Okay, our expectation in the course. If we ever ask you what a single trig ratio is, you can always just leave your ratio with a radical on the denominator. However, if we were to ask you to do anything with that, now multiply that by something, add or subtract it from something, now we need your expression to be in good form. And that's why you see in this example, number 1, we needed to do a little rationalizing on the denominator. So hopefully that just gives you an overview of some stuff. Your chance now is to jump in, work on knowing your special triangles, being able to build your special triangles, and then to be able to determine the proper ratios for each one. Okay, good luck.